This lecture is on the first section of Chapter 5, Normal Probability Distributions. So in this sections, we introduced normal distributions and the standard normal distributions. And in the chapter sections 2 and section 3, you will find probabilities and find values in normal distributions. And the last chapter, the last sections of the last section of the chapter will introduce the sampling distributions and the central limit theorem. This lecture is on the first sections of chapter 5, normal probability distributions. So the first sections will introduce the normal distribution and the standard normal distribution. The second and the third sections will introduce the idea of how to find the probabilities and the values in normal distributions. And the last sections will introduce the sampling distributions and talk about the central limit theorem. So what is normal distributions? Before we can talk about normal distributions, we have to introduce the ideas of a random variable and a continuous probability distributions. So a random variable is a value of a given variable in which represents the outcomes of a random phenomena. Okay, so the outcomes of the random phenomena is considered as a random variable. For an example, if you consider the experiments of tossing 2 coins, and then you can consider that the random variable x to be the number of heads observed after tossing 2 coins. Possible outcomes can be 0 head, can be 1 head, or can be 2 heads. And those outcomes randomly happen as the result of an experiment. And a continuous probability distributions is the distributions of a continuous random variable. So in the first example, the variable number of heads, right, observed after tossing 2 coins is a discrete random variable. And then the continuous random variable, again, it is a random variable of a continuous quantitative outcomes. Here an example, you're serving a random sample from Washington State's populations about their daily commute time. Then you can consider the continuous random variable x to be the responses from the survey. Because the type of the data that you're collecting is a continuous quantitative, and then you're collecting from a random sample. That means the variable is a continuous random variable. All right. And once you have know about the random variable and the continuous probability distributions, then we can talk about normal distributions, right? Normal distributions is a continuous probability distributions for a random variable x that has the following characteristics. So the first characteristics is the graph of the normal distributions has a norm curve or a bell-shaped curve. Okay, the graph of the distributions. And then the mean, because the distributions is a normal curve or a bell-shaped curve, then the mean, the median, and the mode are the same, relatively equal. The normal curve is bell-shaped and is symmetric about the mean, right? Which makes sense. The total area under the normal curve is 1 because we're talking about the probability. And then the total probability of any given event should be, any given experiment, right? Should be 1. And as the normal curve approaches but never touches the x-axis, it extends further and further away from the mean. So the curve we're talking about is this curve right here. So this curve is gonna approach into the x-axis, but never touches the x-axis. Okay. between, and then the last characteristics is between mu minus sigma and mu plus sigma, which is 1 standard deviation away from the mean. The graph curve downward. What it's saying is, so if this is mean, the mu, and this is sigma, right? Mu minus sigma, and then mu plus sigma. So between these two value, the graph downward. The graph of the distribution is downward. And the graph curves upward to the left of mu minus sigma and mu plus sigma. So the point at which the curve changes from curving upward and curving downward is called inflection point. So this point here is the inflection point. It was a IP, right? Inflection point. So these 2 points here are the inflection points. So that means if you can identify the inflection points, you can estimate the value of the standard deviations, because the inflection points are the points that are 1 standard deviation away from the mean. All right. And then another thing is the probability density functions of the normal distribution with the mean mu and the variance sigma square is this formula. So this is PDF here is the probability density functions of a normal distributions. And you can see X is a random variable, mu is a mean, and sigma square is a variance. So this is the normal distribution curve, right? I graph this curve using the PDF functions, which is described here. So I use this curve. I use the mean as 0 and the standard deviations is 1 for this curve, for those normal distributions. And as you can see that, if you want to look at here, right here, when you have, when I try to find the area under the curve from -1 to +1, you can see that you get around 68%, right? 0.68, and which makes sense because remember in empirical rule, 1 standard deviation away from the mean will observe around 68% of the populations. And if you look at the area under the curve from -2 to 2, which says there's 2 standard deviation away from the mean, and the percentage of the populations are observed in between -2 and 2 standard deviation away from the mean is around 95%, which aligns with the empirical rule that we learned earlier. So now, we want to look at the example number 3. So example number 3 show you the 2 graphs of the 2 normal distributions, right? With the different means and different standard deviations. Can you estimate the mean and the standard deviation for each data set? So let's look at the first data set, the fat one here, okay? When you see that you have, I can try to pick the curve. So the peak of this distributions is around, let's say this is 10, so this is like 3 or 4, right? So the mean is around 4. And what is the standard deviations? In order to estimate the standard deviation, you want to find the point, the inflection point, where the curve changing from downward and then upward. So I guess that the inflection points, from my observation, the inflection point is right here and right here. Okay, so these two are the inflection point for these distributions. And then if I can find the distance between these two values, that is the standard deviations. So I say this is like 12, right? So then the distance between 4 and 12 is 8. So for this graph, mean is 4 and the standard deviation is about 8. For the tall, skinnier graph, this graph right here, right? And if you look at this graph, you can try to estimate the mean, which is the peak of this graph. So the mean is around, I can say, is around 10. So the mean is around 10. And how about the standard deviations? Again, I want to look for the inflection point. So it looks like this is when the graph started to change from concave down to concave up. Then I go ahead and plot those points, right? So down here, and then after those points is turning up. Okay. So my inflection point is this point. So then I can try to find the estimation of it. So it's about, let's say 15. And then the distance between 10 and 15 is about 5. So the mean and the standard deviation for the two graphs are found using the graph of the distributions, using the knowledge of inflection point and the knowledge of the mean of the distributions. All right. Now we know what is the normal distributions, then we can discuss what is the standard normal distributions. So by the definition, standard normal distributions is a normal distributions with a mean of 0 and the standard deviations of 1. Okay, mean is 0, standard deviation is 1, is the characteristics of standard normal distributions. And let's review that in section 2.5, we talked briefly about the standard score for each data entry. And finding the standard score, which is the z-score, we take the x is the data entries, right? And you subtract the mean of the data set and divide it by the standard deviation of data set to find the z-score, the standard score. And again, the standard scores is a score that tell you how many standard deviations away from the mean that values lie from the mean, away from the mean. Okay. So then we can use the standard score for each data entry. We can convert each data entry of a normal distributions to its z-score, and the distributions of all the z-score is in standard normal distributions. So the standard normal distribution in this way is a standard, like a standard distribution, normal distribution that helps you standardize all the normal distributions. Remember, if you want to compare the two values or the two distributions, you need to convert it to a standard measurement. And the standard normal distribution is a standard measurement that helps you do that. There's some properties of standard normal distributions. Again, the z-score, the cumulative area, is close to 0 for the z-score that's closer to negative 3.39. What does that mean? I mean, if you have a standard normal distributions here, okay, when mu is 0, right? And then the z-score, so the cumulative area is the area under this curve right here. This is cumulative area. And it is saying if the z-score for the standard deviations is about negative 3.49, then the area under the curves here is very close to 0. That means if your z-score is about negative 3.49, then you are very, very far away from the majority of the populations. So then most values that are bigger than you most data points of the populations is bigger than you. So that's what they say. Okay. So then the cumulative error increases as the z-score increases. So the cumulative area here. So if you look at your left side, right here. Look at your left side, there's almost zero. There's nothing that's less than you. If your z-score is negative 3.49, there's nothing less than you. But then as the z-score, if there's someone else has a z-score that is slightly better, like negative 7.5, for example, so if another data point has its z-value is negative 2.5, then the cumulative area here will increase. So the cumulative area should be the green area here. So the green area increases as the z-score increases. And the green here, the green areas here is a cumulative area to the left of your point. All right. And the cumulative area for z equal to 0 equals to 0.5. That makes sense, right? Because z equal to 0 is as the middle of the populations distributions when mu equals to 0. So then your area here, cumulative area at this point should be 0.5, which is the half of the populations. And another thing is the cumulative area is close to 1 for the z-score, that is 349. Okay. That means if your z-score is about 3.49, most of the populations, most of all the values in the populations are less than you. So you observe most of the area here to the left of you. All right. Again, the z-score get close to 349, right? And everything is close to, everything is not exact. That is because the curve here is never touches the x-axis. So you always have some small little probability that there's someone either less than you or bigger than you. But in general, that's why in general, you always have, not always, but most of the time, you can always have some outliers, right? Some random big values or some random smaller value, and you cannot capture it in your sample. All right. And then as we discussed that if the z-score is in between -2 and 2, then your score or your values are usual scores, usual values. If the z-score is from -2 to -3 or from 2 to 3, then your score is unusual scores, or your values is a little unusual observations within the populations. And if the z-score is less than -3 or more than +3, then the score is very, very unusual. That means the values that you have right there is very, very unusual observations within the populations. Okay, so we want to work with standard normal distributions because, again, if you want to compare the two distributions, if you want to compare the two values that are pulled from two different distributions, normal distributions, then you need to convert them into the standard normal distributions, so then you can do the job. And it's a nice thing about the standard normal distributions is because you can use functions, right, to find the cumulative area of a standard normal distributions. Then you can use, so then in order to find the probability or the cumulative area, under the cumulative area, you can use a table that is called a standard normal table or the Z table to help you find the area under the curve of any of the Z values of any given value. Okay, again, using the standard normal table or the Z table, you can find the area under the curve of any of the Z value. And the area under the curve of any of the Z values here is actually the probabilities of observing a values that is less than Z. Okay, so this area here is a probability of any given values that is less than Z. Or if you convert it to the X value, then it's a probability of X that is less than the X value that you're looking at right now. All right. So let's do some examples and it will make more sense for you. But keep in mind the area under the curve using the Z table is the area to the left of this value. And the area to the left is the probabilities that any observed values that is less than this Z. Okay. So this is how a Z table looks like. So if you look at this table here, you can see that you have Z, right? You have a first column is a value of Z. I always say -0, -1, -0.2, and so on and so forth. And you look at the first row here, it will tell you the probability, it will tell you the second decimals of your Z value, and the first column tells you the first decimal of the Z value. For an example, if I look at this values right here, right? That means my Z values is -0.1, -0.11. So if the Z values is -0.11, then the area, right, the cumulative area to the left of this Z value is P, that is less than Z. So I call this is Z1, right? Z less than Z1 is 0.45620. All right, again, if the Z value is -0.11, then the area to the left of this Z value is 0.45620. That's the area to the left. And since the total area of the normal distributions is 1, then I can find the area, right, the probability to the right of Z1. So Z greater than Z1 will be 1 minus the probability of Z less than Z1, which is equals to 1 minus 0.45621. So knowing the area to the left, which is less than Z1, you can figure the area to the right, which by taking 1, subtract the area to the left. Okay. So that's how you use the Z table. And in the Z table, you have the negative values for Z, and you also have a positive value for Z. And in order to find the positive value for Z, I can take here. Here's a positive value for Z. As you can see that on the first column are the positive first decimal of Z value, and in the first row, you have the second decimal of Z. Okay, So let's pick another value. So if I want to look at the z values when the z values of let's say 2.37, then because my z values is a positive, so it should be z0 here, right? And it should be 2.37 on the right of your distributions. And using this table, you can find the area to the left of this point, right? Let me find, using this table here. And this area here should be the numbers that you can find in this table. So 2.37, 2.3 right here. 7, remember, you have to keep in mind, so it's go from 0 to 7 right here. So 2.37, so this probability is 0.999111. So what does this mean? What it means that the cumulative area to the left of z of 2.37 is 0.99111. Okay, that means the probabilities of picking a values that is less than 2.37 is, so the z, you're picking a z that is less than, let's call it z2. Z2 equals to 0.99111. Very big chance that you're going to pick a values that has a z value that is less than 2.37. Okay. In other words, if you're looking at the right side of this value, so you want to find what is the probability of picking a values whose z's value is greater than z2, which is 2.37, is very small, which is equal to 1 minus 0.99111. Right. So it's about 98800, right? 0.00889. Which is the probabilities of picking a value whose z value, the z score, is greater than 2.37. And that makes sense because the z value right now is very big, it's bigger than 2. That means this values here is already an unusual observation. So the probabilities of finding another value that is bigger than this value should be very small. And this proves this. So this is how you use a z-table in order to find the probabilities under the curve of any of the values, right, given the z value. And this is how you look up for z value using the first column as the first decimal of the z value and the first row at the second decimal of the z value. And then the numbers inside this table will give you the probability to the left of any particular z value.